It's no secret that our distant ancestors were true survivors. Our earliest known relative, Australopithecus afarensis, lived during the Pliocene epoch, between 5.3 and 2.6 million years ago. This was a time of great environmental upheaval with dramatic climate change and the formation of new mountain ranges, but life on Earth somehow managed to not only survive but thrive through it all. And now we have a better idea of how this ancient relative of ours managed to make it through one of the biggest challenges of the Pliocene epoch, an ice age. The study, published today in the journal PNAS, describes a series of volcanic eruptions that took place in what is now northern Ethiopia around 4.7 million years ago. These events caused a rapid climate shift from warm and wet to cold and dry, conditions that would persist for about 1,000 years. And yet life found a way to endure. The researchers used multiple lines of evidence to piece together what happened. They studied sedimentary rocks, soil deposits, and ancient volcanic ash layers at two different sites in Ethiopia, Kanso and Asbol. Volcanic eruptions had occurred there before and since the Pliocene, but the sequence of deposits at these two locations revealed an uptick in volcanic activity during the latter half of the epoch. This included explosive eruptions that sent ash raining down over large areas of eastern Africa, blocking out the sun and disrupting the climate. To date those eruptions, the researchers used a technique called argon-argon dating. Rocks contain argon atoms that are created when potassium atoms decay. As the rocks are exposed to the elements, some of the argon atoms can leak out, but if the rocks are buried, they remain trapped inside. So the ratio of potassium to argon in a given sample can tell us how long ago that sample was last exposed to the air. In this case, the team found that the oldest volcanic deposit at both sites was about 4.7 million years old. Other deposits within that layer ranged from 4.7 to 4.5 million years old. The scientists also analyzed the chemical composition of the rocks. Rocks that formed from magma deep within the earth contain a mineral called olivine, while those that formed from more shallow magma contain more biotite. If there was a lot of olivine in the rocks at the Kanso site, then that suggested the magma came from deep within the earth. And because deeper magma tends to be hotter, the researchers hypothesized that the corresponding climate was warmer. At the Asbol site, however, the opposite was true. The presence of biotite suggested shallow magma and therefore a colder climate. This supported the idea that these eruptions were causing major regional changes in temperature and rainfall. So how do we know that these changes persisted for about 1,000 years? The researchers studied the chemistry of the soils at these sites. Soils that form in areas with lots of rain tend to have a high concentration of aluminum and a low concentration of calcium. But in drier regions, the reverse is true. By analyzing the ratio of calcium to aluminum, the team was able to reconstruct past rainfall levels. They found that the amount of rain changed drastically from the beginning to the end of the Pliocene. At the start, it had been warm and wet, but by 2.6 million years ago, the climate was cold and dry. That climatic shift, combined with evidence of changing vegetation from other studies, suggests that the eruptions had a significant impact on the environment. But just why were the eruptions happening at this particular time? Well, the answer might lie far away. Around the same time, the Sinus Mountains in eastern Africa began rising due to tectonic plate movement. This created a massive mountain range that stretched into what is now southern Ethiopia. While the mountains were still forming, though, they acted as a sort of barrier, blocking moist air from reaching the interior of the continent. Without that moisture, the landscape dried out, which may have triggered the volcanic activity. As the mountains continued to rise, the climate stayed dry. What does all this tell us about the lives of our ancient relatives? It helps us understand their behavior in relation to the environment. According to the researchers, the older deposits from the start of the Pliocene show evidence of both a diverse group of animals and a variety of habitats, including lowland tropical forests, mountainous regions, and grasslands with scattered trees. But the younger deposits show signs of ecological change. There were fewer kinds of animals and the environments were much drier. Yet the researchers point out that these eruptions did not spell total disaster for the region. At Kanso, For instance, a layer of volcanic ash was deposited on top of a stratum containing animal bones. After the eruption, the area seems to have quickly recovered. Small mammals returned and eventually the habitat looked much like it had before. At the end of the day, life was able to carry on despite the huge environmental upheaval. Now the team wants to learn more about how plants and animals adapted to these sudden environmental shifts. Hopefully, future studies will shed light on how our ancestors survived the changing landscape. But until then, we can appreciate just how dramatic the Pleistocene epoch was. Over just a few million years, there were multiple mass extinctions, and the climate swung from generally warm to generally cold. We're just now starting to understand how life on Earth managed to get through all of that. And it's a good thing we're trying to understand it better because we're living through another period of rapid environmental change. If the pace of human-driven global warming continues like today, we could see temperatures rise by 2 to 4 degrees Celsius above pre-industrial levels by the year 2100. And even if we slow down the global temperature increase, many ecosystems won't have enough time to adapt. Understanding how life has changed in the past could help us predict how it might change in the future or perhaps even give us clues on how to mitigate some of the worst effects of a warming world. While studying ancient volcanic eruptions may not seem like it has anything to do with us modern humans, we're part of the story too. Speaking of ancient humans, I recently made a video about a very special relative of ours who lived 300,000 years ago in Siberia. Denisovans are an extinct group of archaic humans who likely had dark skin, dark hair and an ability to adapt to cold climates. You can watch that video right now on Nebula. This video is part of a series where I explore the amazing stories of our ancient relatives. I travel to the places where they lived, see the fossils up close and meet the scientists working to bring them back to life. It's a lot of fun and a great example of what you can find on Nebula, like exclusive documentaries, series and specials that you won't see anywhere else. You can watch all my videos without ads and get other great perks like behind-the-scenes content and a community with other history buffs. Plus, when you sign up at the link below, you'll get a free month of Nebula. It's the best way to support educational creators and get amazing exclusive content. Thanks to all of you for watching and supporting this channel. I'll see you in the next one.